Hello, in this video I'm going to give a brief overview of Feynman diagrams. So these are the diagrams of particle interactions that Richard Feynman came up with just after the end of the Second World War, so in the late 1940s. And yeah, this new approach, it was transformative really in being able to simplify the probability-based calculations that are involved in particle physics and quantum mechanics. So you've got a sort of twofold benefit of these Feynman diagrams. One is to actually visualize particular interactions, and then the other is to simplify the calculations associated with those interactions. So let's have a closer look at these things here. Right, so let's stick in the field of quantum electrodynamics. So that's our description of the electromagnetic interaction. And if you remember, we're now talking about interactions rather than forces. So an electromagnetic interaction is an exchange of a virtual photon between two particles. So that's what we're going to be looking at here. So we're going to be drawing diagrams which have got lots of fermions and photons on them. So let's start with electrons because they've got electric charge. They're fermions. They engage in the electromagnetic interaction. And let's see what they might be doing. Right, we'll build up a selection of Feynman diagrams so we can make them gradually more complicated as we go along. Right, so the first thing with a Feynman diagram is they're a bit like a graph in some ways, where we've got time and space as the two axes. Sometimes you'll have people drawing these with time going from bottom to top. Sometimes you'll see people drawing Feynman diagrams with time going from left to right. I'm going to draw going from bottom to top. You just need to be clear when you're creating a diagram or viewing a diagram which direction time's going in. So we'll have time going from bottom to top in this case, and then space is going from left to right. The space axis is more just we're not trying to quantify how far something's moving in space. We're just trying to show in a broad brush way, is something moving in space? Is it moving towards another particle or away from another particle? So it's more of a just an identifier rather than something we're quantifying. So say we've got two electrons. We've got one electron sitting here at so this is at a particular time. Every horizontal line is a snapshot in time. So we've got two electrons, and we know after some time they've ended up, we've got two electrons here and here. Now, these electrons, they're fundamental particles. They're completely indistinguishable from each other. So if we look at this later time up here, we don't really have any way of saying, oh, well, we'll look at this one and we can now say, oh, well, it's this one here, or it was this electron. We don't know which one's which. So there are a lot of different ways that we can get these two electrons at the bottom to the two electrons that we got at the top. Yeah, we might just have, let's do some different colors on these. We could have this, that electron might have gone to there, and that electron might have gone to there. Or we might have this one's gone over here and this one's gone over here. We've got various things that are going on, or they might interact with each other, which we get onto in a moment. So say we were going to draw those ones out, you could draw your first Feynman diagram would just be simple as we've drawn a line with an arrow on it and a line with an arrow on it. So these arrows are not giving a direction of motion. What these arrows are telling us is whether the particle is matter or antimatter. So if we've got the arrow pointing in positive time, so going upwards in this case, then we're saying it's matter, not antimatter. So if we had a positron, so an E plus, the antimatter equivalent to an electron, then the straight line would have an arrow pointing downwards. So all antimatter points backwards in time, matter points forwards in time. So this is what we've got going on here. So in this case, the electron, the lepton, is a straight solid line. So the lepton, straight solid line, and the arrow denotes whether it's matter or antimatter. We could do a similar thing with cross lines if we were, if this one was moving to the left and vice versa. So what if these things interacted? So what if we had a photon going on? Because what we could have is our two particles at the bottom. These are our two endpoints over here. They could be moving towards each other, because in this top case, you see there's been no movement right or left. So I'm actually saying nothing's changed. These electrons haven't even moved. There's been no movement in space because they're vertical lines. There's just been a change in time. If there had been movement in space, you could do something like this, say, in which case if we drew that with the arrow and that with the arrow, the two electrons have both moved in space because they've shifted in the left-right axis, and they've moved in time because they've moved on the vertical axis. So yeah, two slightly different things here, different diagrams based on the end position. So what if they had ended up, actually let's move these in a little bit, so they've got a different position in space when they finish. So they've started off moving towards each other, then they have interacted, so they've got close enough. So say this electron on the left hand side then emits a photon, which we do a wobbly line for, and then that will, the emission of that photon, because that's going to release, is emitting some energy, some momentum in that photon. It changes the path of the electron, so it's now changing its path through space. It's got a different angled line, and then that photon is absorbed by the other electron, which changes its momentum and velocity. So they've interacted in such fashion. You've got a photon in the middle, so we've got electron with the upward arrows. We got a photon which was emitted. So earlier in time, if we look at what's going on with the time here on the vertical axis, so that is earlier where it was emitted, and that is later where it's absorbed by the other electron. Both interactions with a photon, the emission and the absorption, have changed the energy and the momentum of these electrons, which has changed their path through space, and they've ended up at these other, at the endpoints again. So that could have happened. I mean, we don't know whether we've got this case here where they've just traveled straight from A to B, or whether we've got this case here where they've actually interacted. Similarly, we could have something even more complicated. If we've got the same start and end points, we could have something like, this is going to be hard to draw, but say they had actually crossed, let's say I've drawn these far enough apart really, and then repelled each other that way with a photon going across. So you've still got these intersection points, but now we've got the left-hand electron at the start has ended up being the right-hand one at the finish, and they've still exchanged a photon. They've just done it in a different configuration. And we draw all the arrows on again. So we've got a lot of different ways that we can get these two electrons from the start to the finish. Equally on this one again, this is just labouring the point of how many different ways we've got of drawing these. We could have had that it was the right-hand electron, sorry, that emitted the photon first, and then that was absorbed by the left-hand electron. So you've still got something that looks very similar, but in this case here, you'll see the photons come out of the right-hand side, and this one is come out of the left-hand side. Now, we don't know, looking just at the start and the finish, which one of these interactions has taken place. And this is the value behind these Feynman diagrams, is not only does it give a nice pictorial representation that describes the process of these two electrons coming towards each other, potentially exchanging this photon, or not in this case, just going straight from A to B. So it gives a description where you can just look at it and see what the process is, but it's also showing all the different ways it could happen. And we could draw an infinite number of these. I mean, I've drawn 4 here. Let's ignore this first one where they weren't moving through space, but the ones where they are moving through space and time, we got no interaction, interaction starting on the right, interaction starting on the left, but they're staying left and right. Then we got this one where they're crossing over, but we've got the this electron emitting first. We could do the same thing where that electron's emitting first. We could draw another diagram where you've got 2 exchanges of photons, 3 exchanges, 4 exchanges. You can draw an infinite number of these diagrams, and each one of them will have a certain probability of occurring. So the Feynman diagrams make it a lot easier to sort of cluster these different configurations and to work out the probabilities. It's still quite a complicated process, but they're a really useful tool to make the probability calculations so much simpler. So there's a lot more to a Feynman diagram than just, oh yeah, let's draw out, to describe what a particular interaction is. It's getting into all the different permutations that can sit behind that interaction. So each time you get one of these points here, one of these what we call a vertex, so all of these vertices, all of these junction points, you'll see here we're always going to have 2 leptons and a boson for all of these. So we've got lepton in, lepton out, boson coming out. So that's what's happening in all of these junctions. And at every single junction, everything is conserved. Energy is conserved, momentum, charge, lepton number, all of these things are all conserved in every single vertex, and consequently over the entire process from start to finish. So you're always looking at those conservation laws. So that's what we've got with all of these. So I'll clear this, I'll load up another sheet, and then we'll look at a few more of these diagrams. Okay, so say we had annihilation. So let's look at electron-positron annihilation so we can get some antimatter into all of this as well. So I'll actually draw up, first of all, the 2 electrons, one of the versions we had of that. So say we had that electron, it was emitting a photon, and then the photon gets absorbed. So we've got electron, 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 electron. We've got this photon with the gamma sign going in between. Slightly wonky arrow on that one. All right, so let's take a comparison of this then to if we had a positron thrown into the mix. So again, we've got our time going upwards. That's time going up here. But now we're starting with an electron at the bottom and a positron at the bottom. So they're going to start moving. So this is very similar to what we got at the bottom of this left-hand diagram here. I've just switched over the right-hand electron for a positron, but they're moving towards each other. The electron will have an upwards arrow because it's matter. The positron will have a downwards arrow because it's antimatter. They're both moving through space because we've got the slanting lines and moving through time. Right, so as they get closer, just as happened here, they get closer, and then the left-hand electron, all right, it could have been either of them, as we saw before, emits a photon. We're going to get the same thing happening here. But in this case, because they're opposite charges, we know they're going to attract each other. So we know this electron is now going to start moving towards the positron. But the photon that it's emitting is then going to come out at a different angle. Everything has to be conserved at this vertex. But you can see that this initial photon emission is just the reverse of what's happened in this repulsion over here. It's got to a point that an interaction is going to take place. So one of the leptons emits this photon, but rather than the electron moving away, now the electron is moving towards. So again, we draw in because it's the electron. we draw in the arrow point, so it's going upwards. Now this electron is going to interact with the positron, so we're going to need another photon coming out. So we have to have two photons in this interaction in order to maintain all of our conservation laws. But you can see how this is very similar to the repulsion diagram, but we've ended up with two photons being emitted. And you have to have these two photons, as I say, for all the conservation laws. We could have drawn this the other way round, where it was the positron that was emitting first, in which case we've now got, see the arrows, the direction of the arrows isn't actually changing in this. It's just saying that now you've got the positron there in the middle section because it's a downwards arrow, whereas here we've got the electron in the middle section because it's an upwards arrow. And in this interaction, this annihilation, so, and let's just unpick exactly, made that a little bit close to each other, exactly what's going on here. So you really have to remember that these arrows are not giving you a direction of the process. The direction of the process is going up the page because that's how time is changing. So at the beginning, we've got an electron and a positron. That's what's happened at time 0, electron and anti-electron, electron and positron. These are moving through space and time as time goes by. So by the time we've got to this point here, they are close enough to engage in this interaction. They're close enough that they're going to, in this case, the electron is going to release this photon, which is mediating this interaction between the two of them. Then a little bit later on, we've got a second interaction between the two of them, where another photon is being emitted. By the time we get to our end time, when we look afterwards, all we've got up here is photons. We've just got two photons at the top. So we've started with electron plus positron. We've ended up with two photons. So following these arrowed lines is not saying, oh yeah, we've ended up with a positron at the end of it all. No, because this is the start and this is the finish. So if we were going to write this out in an equation, we could say we got electron plus positron. That's going to go to two photons. That's what's going on. We've got exactly the same thing in this bottom diagram as well, because everything's moving up the page. It just happens to be that the photons are coming out in different order. And yeah, you can build up, just as we did with the other ones, you've got an infinite number of permutations of these. Yeah, you won't know which one of them has happened. You just know what you started with and what you finished with, and the probability of different things having occurred in between. So yeah, that's just a brief overview. I don't want to spend a lot of time really on Feynman diagrams. There are going to be probably better videos than I'd be able to put together on this. It's not my specialist area of physics. This is just giving a very quick overview of their uses, roughly how to interpret some simple ones. And it is more than just the picture. There's a big calculation side behind all of this. So this is all really I'm going to say on Feynman diagrams in these videos, at least for now. I mean, maybe I'll come back to them in the future. But there's plenty of other resources out there if you're particularly interested in these to go and research it a little bit more yourself. I'll just come back to add something that occurred to me as soon as I clicked on stop, and that is a quick clarification that we can add now to this idea of virtual particles. So I mentioned this before in interactions. In this case, we've got photons, which are the mediators of the electromagnetic interaction. And the difference between a photon and a virtual photon. And I was saying about these virtual photons that you just couldn't get at them because they were locked away inside the interaction. So you can't see these virtual photons because they're locked away. Right. Well, let's compare these two Feynman diagrams here. On the right hand side, we've had this annihilation of the electron and the positron. So we've started with this matter down the bottom, the electron and the positron, we've ended up with two photons. These two photons have been emitted. They're not virtual. These are things that are then detected. They've been released into the world. Not so on the left-hand side with this interaction between the two electrons where they've repelled each other. This photon here, this is a virtual photon. We can't get hold of this. It's necessarily bound up inside the repulsion between the two electrons. So we've got a distinction going on between these, this annihilation of matter into energy, and then that energy released as these two photons, and it's released out into the world, between this virtual photon, which is transferring energy and momentum between these two electrons, which are interacting on the left hand side. So we've got a virtual photon over here, but not on the right hand side. So I think that, you know, adds a little bit of life, I think, and makes it easier to see maybe the basics of these virtual particles.